Thank you so much. So now it is my distinct pleasure to bring up Robert Smith from the team to talk about some of the work that's being done with both Quil, the compiler, XY gates, and a few other things. Robert?
A little bit, yeah.
Thank you.
Can everybody hear me fine? Cool. All right, so I want to, we've talked a lot about the hardware. We've talked a lot about how to actually start using a system and delivering it on a platform. I want to get to a point where we can discuss, supposing you've maybe made a proof of concept solution to your problem, how do you actually turn it into something that's practical, something you can actually run, something that's actually solving problems? I would say that my role at Rigetti is largely attempting to answer this question. In my opinion, the dominating thing that determines how you can take something like a proof of concept, whether it's an equation, whether even you wrote a little proof of concept program, in my opinion, the dominating factor for this is quite simple. It's performance. If your proof of concept works out of the box because a system is sufficiently performant, then you're good to go. If it's not, then you need to do work to make this proof of concept more performant. I see three different sources where you can extract performance. One, which is typically not under the control of a software developer, is the hardware. I would even say this is perhaps the dominating factor for performance. The better hardware gets, the better your software is going to run. But of course, it's not the only thing. The software itself has to be performant. Maybe this means using fewer gates. Maybe this means the application platform is more efficient. You can shuffle data around the internet faster, whatever. It also means that maybe software itself can be used to make more efficient your own software by way of things like compilers or profilers or debuggers. The last source of efficiency is, of course, the user, you, with all your domain knowledge. You know that in chemistry, there are probably not atoms talking across the universe, and you can make approximation, two-body approximations and the like. Using your domain knowledge and your expertise and your smarts, of course, you can deliver more performance to your application. So I want to talk a little bit about our strategy to sort of achieve these things. I would say that here at Rigetti, our strategy is twofold. We want to provide intelligent tooling that lowers the barrier to entry or performance barrier altogether. We want to provide that, but we also want to provide exquisite control of our system. If we can give the user more control, then perhaps they can get more performance out of it. I sort of put a little simple tagline about this, which is, ideally you would not worry about the details until you need to. If you can write your application ignorant of as many details as possible and you can think about just the problem at hand, that's ideal. But when push comes to shove and you want to have extra control over the system or application or what have you, you ought to have that. So we sort of have these two levers, leveraging software, intelligent software, and leveraging you, yourself, the user. And this leads to this sort of two-pronged approach. Intelligent tools sort of push forward this ideal of writing software, which I would kind of call the sort of DWIM, do what I mean. You want to write down the gates that you want to do. You want to write down the measurements you want to do. You just want to write down the computation, which is your proof of concept. That's what you mean, and that's what you want to happen. Tools that make this possible are things like automatic compilation. You just want to feed your things to the compiler and hopefully get the best result out of it. Ideally, the resources are automatically managed. You're not dealing with tweezers and toothpicks and figuring out what gate on what qubit within which part of your program, ideally, again. And then lastly, we can probably add, or we could add algorithmic domain knowledge. So if we sort of codify aspects of the domain in which we're working, say chemistry, optimization, machine learning, what have you, and we can install that into software, naturally we get performance benefit. So the analogy I like to make is this is somewhat similar to Python. In Python, you're not doing any of this crazy stuff. You're writing typically the program you want in relatively simple syntax. Doesn't necessarily mean you're going to get the most efficient result at the end, but there's definitely a great deal of developer efficiency and so on. The other side of the coin is these power tools that you could provide to the user. This has a very other distinct philosophy, the sort of do as I say philosophy. You want to say exactly what you want to do. This means you want to manage resources. You want to manage what's happening to each of the drive lines of the QPU. You want to manage how long things take, when things happen, and so on. It's a very imperative approach to writing software. This is more akin to writing C for anybody that's written C or assembly for that matter. You have very fine-grained control. Yes, it does mean you can shoot yourself in the foot. Yes, it means you can get completely nonsense results. And yes, sometimes it means it's very difficult to prove what you did is correct. But with the control, you can often get an extraordinary amount of performance. So I want to talk about these two things, and I'm going to frequently come back to this picture, so don't feel like you have to memorize it all in your head. I'm going to talk about the smart tooling with our compilation. I'm going to talk about and introduce Quilt, which provides analog control. And then I'm going to, almost like a little bit of a case study / example, I'll talk about tuning up a new gate and how that sort of helps you write software. We're going to start by talking about the thing that all of this is revolving around, which is Quil. It's sort of the thing that ties everything together. I won't belabor Quil. I think many folks in here who have used PyQuil are familiar with the fundamentals, so I'm not going to go into tutorial mode or anything like that. Just list some salient points, especially points of differentiation with other quantum programming languages. One thing that we've wanted in Quil for a while is, and indeed that exists in Quil, is to lower the amount of effort it takes to convert some mathematical representation of your problem into actual code that can run. Originally, when Quil first came out in 2016, we had this def gate feature. It's a feature where you can give a name to a gate and you write out all the matrix entries as you'd find it in a textbook or in Mathematica or whatever. And you can just write it in your Quil program, and automatically you can use that gate within the rest of your program. It turns out this is a surprisingly useful feature. I don't know how many people have stumbled with various different quantum programming languages where they can't define a gate, or if they do have to define a gate, they have to figure out all these little parameters to tune and all these angles and they have to draw a picture of the block sphere and whatever. Here you can just write the gate matrix. Two other features that recently came out are defining gates by way of their permutation matrix. So if you have a logical matrix, often this happens when you're defining an oracle or you're going through quantum computation 101. You can just define it as a permutation. You don't have to write out this big 0-1 matrix. And in fact, if you write it that way, it actually doesn't matter if you write as a matrix or as a permutation. The compiler will understand in either case when it is a permutation matrix, and it'll be able to work with it more efficiently. And the QVM, the simulator, also recognizes that and will be able to execute more efficiently. A final feature, a final way to define a gate in the language is actually through its representation as a polysum. So this happens in many different domains, in error correction, in chemistry, if you're defining Hamiltonians, all of that. You can define it as a polysum. You write down the terms of the polysum along with their corresponding coefficients. These may be scalar coefficients. They might be parametric. In this case, for the swap gate, we have a little parameter there, and then we write all the polyterms. It can be 1 qubit, many qubits, it doesn't matter. You write that out, and the compiler will actually, again, be able to use that representation profitably in the compilation and execution of the program. Another thing that Quil has that really ties to our hybrid approach to computation is a collection of classical data types. The data types aren't there just for the sake of being there. It's not that, oh, well, I have a programming language and I want to have an integer. It's that these things are the fundamental units of communication between your classical processor and your quantum processor. Gate angles, for instance, are things that you're going to change and modulate. What we heard from Xanadu earlier, oftentimes these gate parameters are what you're going to feed into your program itself. And we've taken very great care to have our compiler and our SDK in general support this mode of use. Likewise, we have integers, octets. Octets are very useful if you're like a hardcore C programmer and you want to write out the memory map for everything that you're using. And it's useful when you're also a company that builds the control systems on top of which this memory is being partitioned and allocated. Quil has very simple syntax. I know this is a bit subjective. but there's not really much noise in the program. You don't have superfluous semicolons and parentheses when you don't need them. All of that stuff, it's pretty clean, which means that Quil is rather easy to generate. If you're writing a little program, you can write a little Python script or Perl script to just dump out a Quil program. It's not very hard. You don't have to worry about a lot of syntactic nuance. Quil also has support for these things called pragmas. Pragmas, I don't know, maybe they followed a fashion like the 1990s or something. They still exist. If anybody's used OpenMP for parallelizing their C or C++ code, you write a little pragma above the loop, and you say you want to parallelize this loop, and these are the loop indices, or you want to collapse these for loops or what have you. Pragmas are a way to introduce additional information to the compiler so that the compiler can use this. In this case, we see that there's a pragma for preserving a block, which means, hey, I know what's happening in this block. Compiler, don't try to rewrite it. Don't eliminate these identity gates. Maybe I want those there because they provide a little padding or spacing. Compiler, yes, I know these X gates right here can cancel each other out. Don't do that. So pragmas provide an extra degree of control. You can ignore pragmas, and the program should still make sense, to be clear. And in this case, if we eliminated the pragmas, the program would indeed still make sense. Lastly, Quil has very exquisite support for control flow. In fact, it has a complete suite of, I call it RISC-style control flow, RISC as in reduced instruction set control flow. These are the types of primitives you'd find in an assembly language. So you can conditionally and unconditionally branch based off of the aforementioned data types and so on. So in this example, the bottom half, after I do that Hadamard gate right there, we're doing something that looks like an active reset circuit. We're measuring it, and then we're jumping and flipping it back to the 0 state conditionally on the measurement. So we can express those types of things. The biggest point, however, that I want to make is that Quil, it's a portable language. It's not designed explicitly to target our specific QPU. As David said earlier, Quil is the thing, at least logically speaking, that our machine runs. However, Quil's design isn't inherently tied to our QPU. With that said, in our tooling, in our infrastructure, in our software architecture, hardware architecture, we've attempted to optimize for Quil's execution. So I want to talk a little bit about the compiler. I think it's one of the greatest pieces of software that I've ever been able to work on. It's for somebody who is interested in math, computer science, algorithms, and physics. It kind of is all of that at the same time. I'm not going to talk about every single feature of it, but I do want to talk about conceptually the model that we think about the compiler. So our compiler is called quilc, for Quil compiler. Surprise, surprise. It takes 2 pieces of input and only 2 pieces of input. It takes your program that you want to compile, which is Quil code, and it takes a description of the thing you're compiling to. What does that look like? We call it an instruction set architecture, or ISA. That's going to consist of the gates you're able to execute, how they're connected, how many qubits you have, in some cases, how good the qubits are, how good the gates are. It's a description of the machine you're compiling to. You take those 2 pieces of information, and out comes a compiled program. The way quilc works in our SDK publicly right now is the program will come out also as Quil code, but each of the instructions in this Quil code will be native to the architecture you're running on. In this case, we're constructing a little Bell state on qubit 0 and 2, and it compiles it to the right architecture with the native gates for which it was compiled. I said a moment ago that this ISA description can take in not just the gates and the qubits themselves, but also a description of the noise of the machine, or the fidelities of the gates, or the coherence time of the machine. If you provide that, which is totally optional, if you provide that, the compiler is going to attempt to use that information to make more informed decision-making about better qubits to use, better ways to arrange your gates. It checks how often particular 2-qubit gates are used on particular parts of your qubit lattice, and tries to arrange for those gates to be arranged on the better qubits and so on. So we generally call this, sometimes we call it fidelity-aware compilation or approximate compilation. And it's something that's just built in. You don't have to think about how to turn it on, how to make it work, or anything like that. You just provide the information as a part of the ISA. So like I said, quilc does a lot of things. I did want to state a few things that quilc does in consideration when it compiles your program. It does have many routines for doing optimal compilation. So there have been some results in literature to optimally compile certain gate sequences or certain programs into the fewest number of gates, and it has some knowledge of that and exercises it naturally as a part of the compilation process. It also has a relatively advanced term rewriting system. For those familiar with term rewriting, it maybe doesn't sound super glamorous. The thing that's interesting here is how it decides which term rewriting, which rules to use to do the term rewriting, and how to algebraically apply those things. It has state-aware compilation. This means if the compiler is able to do it, it will take into account the fact that your program is going to start in the 0 state, and it will actually partially simulate your program, attempting to find a gate sequence which is equivalent but shorter. Obviously, you can't do this infinitely. There's a certain bound where the compiler says, okay, I give up, you've entangled too much, I'm not going to try to simulate more. But when it can, especially at the beginning of a program and especially after measurements, it's able to do those things. One of the things that it can detect, for example, is if your state is an eigenvector of the operator within your program, and it can just eliminate that entirely. And so you can see very dramatic reductions in gate count when this optimization is applied. We also have control flow optimization, so this is more for the classical compiler geeks. Quilc, it's a compiler. It constructs a control flow graph. It tracks resources across that control flow graph, collapses edges, eliminates dead code, all of that. So it's okay if you have code that will never be run in your program because it'll just get rid of it. Lastly, what I said earlier is that it has fidelity-aware compilation. It will take into account the coherence time of the qubits and the relative measure of the time of each of the gates, and it will take into account the fidelity of the gates themselves to attempt to produce more informed decisions. So just as a little fun thing, it's not expected you're going to read this, but there's a little flag on quilc that actually shows you every single decision it thinks about when it's compiling a program. So this is actually a medium-sized program, and you can see all this stuff scroll by if you're interested in that. Very useful as a debugging tool for the compiler when something doesn't work. You can find a rewrite rule or something that doesn't work. And then finally at the end it gives our result. For those who want to do that, you just do -- verbose on quilc when you run it, and you'll get that. Last quick mention, quilc, it's a completely open source program. It's something that we gladly accept contributions to. We've found new employees through it. We've gotten extremely good integrations with other software. A lot of people are writing specialized compilers for certain kinds of gates, and we're able to integrate that in a very open fashion. And so you can find that on Rigetti's GitHub. So now I want to move into a little bit about Quilt or Quilt, you'll hear both of those, which is our pulse level control or allowing users to do pulse level control within their Quil programs. So Quilt, it's an extension of Quil. It's a proper language extension. It's not a separate tool. It's not a separate API. It's not a separate anything. It's an extension of the language itself. And the onus is on us to, of course, make tooling to support this thing. But it's a language extension. So that means if you're writing Quil, you can actually just add Quilt code directly to it. It's not a separate thing whatsoever. In this case, the user can control everything almost everything that they would want to control. This means the shape of the waveforms that gets sent down any of the drive lines, how measurement is performed, tuning different parameters of these waveforms that are sent down. We call this, changing the frame of reference. This includes frequency, amplitude, phase, all of that is controllable. Interestingly, the way in which you introduce this into your program is typically by providing a gate calibration. So usually you've already written your program in terms of unitary gates and measurements. And what this allows you to do is say, okay, this gate that I've already written in my program, interpret it as this low-level control of the hardware. It turns out to be a very, very good interface and allows you to take existing programs without having to rewrite them and experiment with pulse level control. It's currently in alpha testing. Our tooling supports it. We're going to see a little demonstration of this a little bit later from one of our first users from Horizon Computing. And we plan on making it more broadly available. Just out of a little bit of curiosity, Quilt, the name comes from Quil plus time. We really like this Quil plus letter thing, or at least I do. So a little bit about what's in Quilt. I'm not going to exhaustively bore you by reading each line of the table. There are basically three categories of things in this table. There are ways to define new things. The principal objects that you're using in Quilt are defining frames. This is sort of state that's tracked across the execution of the program, which includes phase, amplitude, all of that stuff. Defining waveforms, it's literally what it says. And defining calibrations, which means how do we go from the pure mathematical domain of gates or measurements and convert that into analog controls. And a calibration is that explicit bridge. The next few commands, the shift and set commands, shift phase, set scale, set frequency, shift frequency, and so on, are, again, exactly as it says. It allows you to change the frequency on this frame, allows you to change the amplitude of the waveform that's to come out completely dynamically. In the middle of your program, you can change this. It doesn't need to be set ahead of time. And then lastly, the two powerhouses of the actual actions that you can do, the actual interactions with the quantum system, are pulse and capture. Pulse, again, exactly what it says, means fire pulse. In particular, you're going to provide it one of these waveforms and one of these frames on which to fire the pulse. And then capture, of course. How do we listen on one of the lines and capture data, process it? There are ways of providing different kernels for doing classification of the IQ values that come out, turning it into a binary result that's completely compatible with the Quil memory model. These are all commands that become, that are part of your sort of arsenal within Quil. And again, they're the same, it's part of the same language. So here's a little example of calibrating an X rotation by pi over 2. It's relatively straightforward. First, we're going to fence off everything. We're saying nothing in this region can execute simultaneously on qubit 0, meaning anything that happens on qubit 0 either has to happen strictly before or strictly after. We're going to scale our drive line here, which means we're going to set the amplitude of the pulse that's coming out. And then we fire a pulse. We provide a standard library of pulse shapes if you don't provide your own pulse shape. There are some parametric ones that are included by default. In this case, this is a drag Gaussian with all of those parameters. And that's what a gate means. If we want to tune some other gate, all we do is this def cal with another gate. You can do parametric gates. You can do gates. In this case, this is a gate with a fixed angle. But it doesn't need to be fixed. You can use a variable in the body of the calibration should you want that. So taking this example a little bit further, I want to touch on the XY gate. The XY gate, as I see it, and as defined in the Quil standard language, in the Quil standard, is defined by this. Nico earlier described the actual hardware interaction of it. From a unitary perspective, this is how I define it. I want to talk a little bit about why the XY gate is so special. And one way to approach how we might determine a gate is, quote, special, unquote, or how special it is how good it is at representing other programs. So for most 2-qubit gates, like the CCNOT gate, for instance, it's relatively well known that you need 3 of those CCNOT gates to represent any other 2-qubit gate at all. Not in all cases, but in most cases, you need 3 of those gates. So we might measure how good a gate is by how many gates you need of that particular gate, of that particular 2-qubit gate, to represent any other 2-qubit program. More mathematically, if G is our gate of interest that we're interested in measuring the specialness of, the question is, if we only allow 2 invocations with any 1-qubit gate sandwich in between. In this case, U, V, W are tensor products of 1-qubit gates. If you're allowed to sandwich any of those, but you're only allowed 2 invocations of a 2-qubit gate, how much of the space of PSU4, the projective special unitary group, do we actually get from this expression? Roughly speaking, if we were to draw a random element out of PSU4, what's the probability that we could express that element in terms of this expression? So I made a little handy table here. On the left is going to be the gate G, and on the right, it's going to be that percentage, that occupation percentage. The higher the number, the better, of course. So we'll start off with very common gates, CNOT. It turns out that if you're only allowed 2 CNOTs with any 1-qubit gate sandwich in between, the probability that you'll be able to represent any gate in this space is 0. Does that literally mean 0% of the gates are representable? No, not at all, of course. I mean, CNOT itself is a gate that you can represent with 2 CNOTs. Nonetheless, most of the gates aren't representable, which means it's very likely, in fact, it's 100% likely, that you're going to need 3 CNOTs if you're going to compile some 2-qubit program. CZ's in the same boat. I would quiz you guys why that's the case, but I'll get to the punchlines, because CNOT and CZ, they're the same. You put Hadamards on either of the lines of CNOT and you get CZ, vice versa. So it's not as, you get the same result here. CZ happens to be one of the native gates that we've deployed on our Rigetti system since the very start. But that's the result for that. iSwap, same thing, 0%. So maybe we're thinking like, okay, maybe it's always 0%, so what we're going to do is take a parametric gate, a gate where we can range across any number of parameters, and C phase is one of these natural gates that comes with superconducting qubits. And it turns out, this was very surprising to me when I learned this result, that C phase with an arbitrary parameter still draws you 0% of the space, which means on average, you're going to need 3 of these gates in order to represent a 2-qubit program. Where it gets interesting is with XY. In the case of XY, we see that now we have a non-zero percentage. In this case, XY at a single fixed angle, this magic angle, we get this percentage, about 75% of the entire space can be represented if you just tune up this one single gate. So if you're building a quantum computer and you're interested in building a gate that lends to efficient compilation, you ought to tune up just this gate at just this angle, and that means 75% of the time you'll be able to compile a program using 2 gates instead of 3 for 2-qubit programs. That's a huge savings. For all of this stuff, that means your program on average can save 30% or 33% of its 2-qubit gates when this enacts. However, if we tune up the entirety of the, if we tune up the entirety of the XY range, then we get 96% of the coverage of the entire special unitary group of dimension 4, which means that on average, 96% of the time, you only need 2 invocations of this gate with any sort of parameter added to it, as opposed to 3. And I think that's a marvelous result. This was in a paper that my colleagues and I recently wrote. Right now, we do not have built into the compiler the construction of this yet. It's something that's in development, but it is it's a very neat result, I think, in terms of compilation. So let's switch gears a little bit and discuss, we've established through some theoretical means that we want this gate. We want XY. And we know that the hardware that we have, in principle, could support it. How do we actually get that gate to be something that we can use natively in our system? Well, there are 2 things that we're going to need. We're going to need the mathematical representation of this gate. When we write a program, we have to assign mathematical semantics to this thing called XY. And we do that by defining a gate. In fact, we're using this def gate as polysum feature of Quil from earlier. We literally just write out the equation, and it's just an XX plus YY interaction. We decide that we have these little factors in there. It would be just as good if we didn't have that negative 1/2 factor in there. We provide the mathematical representation. That's half the story. But we also need to say how to realize this gate on hardware, and that's where Quilt comes in. So we say that if we have, we define our frame for running these pulses, We define the waveform. There's a special shaped waveform that we need to fire down the drive lines, which looks like an I-swap interaction approximately, if I remember correctly. And then we define the actual action that ought to occur when we run an XY gate. In this case, it's boiling down to blocking off all the other qubits, firing the pulse. This is, if you remember earlier when Nico was describing the XY interaction, there were 2 gates that you had to do. You see those here. There are these 2 pulses. And then sandwiched in between and after, there are these frame rotations that we have to do. So we have these phase shifts after, which are equivalent to RZ gates on our platform. That's it. That's the definition of XY. I elided, of course, all these IQ values. I don't know if that would be interesting to anybody. But that's all you need to write. So now we have those 2 things, a mathematical representation, that's good enough for the Quil compiler, and then we have the physical realization, that's good enough for our control electronics. You have those 2 things, and the gate is now available to you. So going back to this 2-pronged approach of approach to software and efficiency in our software, we can kind of put into context now the things we discussed. Quilc, it removes the need to care about the particular details of the architecture. Indeed, even today, all of us saw many different instances of architectures. We saw our old Agave, Acorn, Aspen. We saw some chips that are in development now that are coming out in the future. The compiler removes the need to care about exactly which one of those is running at any time. Your program that you wrote once should still work on all of them, provided it has enough qubits. It does the grunt work of a lot of algebraic simplifications unless there's a bug. And yes, there have been bugs where things would not algebraically simplify. But you shouldn't have to worry about 2 Hadamards in a row or 2 X's in a row, or if you have 2 RX gates, it'll collapse the angles into 1. Tries to do as much of that work as possible, not unlike a computer algebra system. It can intelligently use coherence and fidelity information, as I discussed earlier. And it understands control flow. But most importantly to me, it's all completely automatic. You don't have to assemble a pipeline of compilers. You don't have to assemble a recipe or a list of rules to make these things enact. It all works just right out of the box. So what this allows you in turn is to sort of write the simplest program possible. On the other hand, I introduced Quilt. And this sort of takes the role of being a power user feature. It allows you to control every drive line, every waveform, just about every photon that enters and exits the system, up to quantum mechanics, really. And it gives you ultimate control. You can define exactly every instant in time, everything that happens with the control system. So that gives you an enormous amount of power. It would seem that both of these things are kind of headbutting each other. On one hand, if we stay in the domain of pure mathematical niceness and nice unitary gates and everything's a linear operator and there's no noise and whatever, the compiler can do a wonderful job optimizing and make your program short. On the other hand, if you define everything in terms of pulses and waveforms and frame shifts and frequencies, the compiler is not going to know what the heck to do with all your stuff. I mean, it's just a bunch of gobbledygook at that point. So it seems like we have to sort of pick a side here. Like either we're going to write our program in a very pure mathematical sense and let the compiler do as much work as possible, or we should have as much power as we can and just take matters into our own hands and do that. What has been very interesting to us is this sort of, it wasn't apparent to me when we first started on this, is actually what happens when you combine both of these facilities on sort of this bigger picture. So, that's kind of what this diagram now represents, is this whole thing. What does that mean? So, when you learn, or when you've written a new feature, or a new gate, a new interaction, what have you, Quilc is able to use this information profitably. If you teach Quilc about the thing that you developed, that you tuned, maybe, you had fun over the weekend scanning over every frequency and you found just the right one. Maybe that was for the XY gate. You found that right angle and it's great and it works and it's super high fidelity and so on. If you tell Quilc about this, it's able to incorporate this into its sort of working knowledge. Quilc is a vast repository of not just mathematical compilers, but information about how gates decompose into other gates, how they're allocated, and so on. And so what I want to show is just a little contrived example that fits on a slide, which is compiling something that looks like a Toffoli program. So here let's consider a chip topology which is just linear. We have this linear topology right here. That means that every qubit can execute some of the single qubit gates, and then every edge here can execute some 2-qubit gate. And the program that we're going to run is we're going to run 3 Toffoli gates successively on successive triples of qubits. In the table that I'm going to show, what we're going to do is we're going to vary the 2-qubit gate that we consider native to our platform. And we're going to start out with the default that we have here in Rigetti hardware, which is the CZ gate. And we see that after compilation, that program, that 3 Toffoli gate program, requires 40 CZ gates, 42 qubit gates. If we do XY gate, we see that the number increases to 49. Well, why is that? Well, the proof that we require only 2 XY gates as opposed to 3 is this proof in symplectic geometry and topology and whatever, and the compiler doesn't magically just learn that information. And we've built the compiler so that it knows a lot about CZ gates as our default. So we get a little hit. So we could write a little bit more software on the compiler and realize benefits. However, something that I think is quite unique to our compiler is what happens when we allow both of these gates on any of the edges at the same time. So if we allow CZ and XY simultaneously, the compiler is able to use either of those, and indeed on our platform, both those gates can be native to the platform and because we introduced it as a Quilt primitive. We see that the compiler synthesized something which was better than either of them separately. That in and of itself to me is an amazing thing. It's amazing that we can figure out sometimes it's better to use CZ here and sometimes it's better to use XY here, and the compiler can figure it out. We can do a little bit better because the compiler doesn't really know anything about the Toffoli gate right off the bat. So what if we just told it? What if we looked up in one of our textbooks or whatever some optimal decomposition of CCNOT which the compiler was not able to figure out? So here we have an expansion of CCNOT. We can tell the compiler that. Note that this uses non-native gates. It doesn't respect any particular topology. It's just a piece of knowledge about CCNOT that we're introducing to the compiler. And it has 6 2-qubit gates. So let's tell the compiler that and rerun our computation. In this case, for CZ, we see we had an improvement. That's good. That's to be expected. It used some generic compiler to compile Toffoli before, and now we've given it additional knowledge and is able to use that. Still with XY here, it's not quite as good. Why is that? Well, each of those CNOT gates in the decomposition that we provided itself would expand to 2 XY gates. And if that's the case, then we're losing something here. So it's not quite as good. However, when we do both CZ and XY with that decomposition provided, the same program in the top left, we've reduced the gate count, the 2-qubit gate count, by 40%, which is an incredible reduction in the number of gates, especially for near-term applications, especially for things where performance is really, really sensitive. I've intentionally chosen something with a few number of gates, not like 10,000 or 100,000, because these small number of gates matter for near-term applications. So we see this interaction. We've tuned up the XY gate. We've told quilc what this gate means from a mathematical perspective. We've told our control system through quilc how to execute this gate. And immediately, by doing those two things and then telling quilc, hey, now you can use this gate in addition to the CZ gate, we get a 40% reduction. Just so I'm not mincing my words, I'm not claiming every single program you write is going to get a 40% improvement. But the CCNOT example was literally the first example I pulled out of my hat. And indeed, these results, when we apply it to QAOA graphs or other things, we see similar numbers. So in this case, we achieved performance by sort of this interplay between having exquisite control of the system and having intelligent tooling that's able to make use of it. Like everybody here, I'll be around all day. I love talking about this stuff. I love our SDK. What I'd like to do now is hand off to Joe Fitzsimmons from Horizon to talk about some of the things he's used this for, Quilt in particular. Thank you, everybody.